Tell us something about Ript. Ript, it's a solution for firewall management on Linux systems, and well, ready when you are.
Okay, Dankeschön. Guten Tag, mein Name ist Lindsay Holmwood. Ich bin Engineering Manager und lebe in den Blue Mountains nahe Sydney, Australien. Ich habe darüber nachgedacht, den Vortrag auf Deutsch zu halten. I can't actually remember the rest. The only German that I was actually taught in school was Waldorf ist doof und das ist meine Hamburger. So I'm going to do all of this presentation in English, but thank you for putting up with my terrible German. So as I said, my name is Lindsay Holmwood. I'm Oxesis here on Twitter. I'm an engineering manager at a company called Bulletproof Networks in Sydney, Australia. But I don't actually live in Sydney. I live in this other area called the Blue Mountains. Unfortunately, the contrast isn't so good on this, but it's there's sort of like lots of big canyons just here, and it's sort of described as the Grand Canyon of the United States, but with trees. So you might know me from a couple of other projects. So I originally created Cucumber Nagios, which allows you to write monitoring checks for Nagios in natural language. Visage, which lets you graph statistics collected from CollectD in the browser using SVG. And Flapjack, which is a monitoring, alerting, routing system. But first up, I really want to thank everyone here at OSDC who's put on this fantastic event. They treat their speakers very, very well, and I can highly recommend submitting a talk for next year. So let's have a look at Ript. So the story actually starts for Ript back in 2008 at this other little conference called linux.conf.au. And in 2008, it was being held in Melbourne. So at the time, I was there, and I was there with a friend named Matt Moore. He works at Atlassian in the host operations team there now. And he presented this interesting scenario to me, which was, he was working at Bulletproof at the time, the same company that I now work at. And Bulletproof does infrastructure as a service and managed hosting, primarily catering to enterprise and government customers in Australia. And we have a bunch of sort of well-known customers within Australia. You probably haven't heard of us here, but maybe you might have heard of some of these guys, primarily Foster's, which is terrible Australian beer. You should absolutely not have any of it. So they had an interesting problem from a technical perspective. They have multi-tenant firewalls, and there are lots of rules per tenant. So you have multiple customers on the same firewall pairs. These are physical firewall pairs. So there were existing rules for, existing tools for describing what those rules were, but that tool sort of built those rules in a bit of a dumb way. So lots of sharp edges to it. And the most important thing from a business perspective was that from a rule application, whenever we were applying rules to the firewalls, it would actually involve downtime. And what was even worse for that was that changes for a single customer would actually cascade and flow onto all of the other customers as well. So this is a pretty bad thing from a business perspective. And you end up with a situation a little bit like this. Yeah, so it's great if you are that customer that is getting the food, but everybody else is sort of boned. And on top of that, the rule application time was quite linear. So it meant that the more rules that you added to the firewall, the longer it would take. And on top of that, the rules, customers that were added towards the end of the life cycle of a firewall would actually have more downtime than customers that were provisioned at the very beginning of that firewall. On top of that, the tool sort of lacked a lot of expressiveness when it came to describing what those rules were. Very brittle, very error-prone. It would basically let you do relatively silly things, and it would just blindly apply those rules, and you end up taking down the firewall pair. So not particularly good. So Bulletproof were basically looking for a tool that would compartmentalize those changes. So whenever you're making a change for a single customer, it only affects that single customer. And primarily, we really want there to be zero downtime when we're making those changes as well, especially for all of the other customers. But it would be really great if we could do that just for that single customer as well, and as little downtime as possible. And on top of that, we really needed a friendly language for describing what those rules were, and preferably with some sort of shortcuts to reduce the amount of repetition. So dry, don't repeat yourself. And ideally, there would be some sort of error checking or validation in that as well, so people can't put silly things into the rules which will go blindly applying. So this idea was sort of presented to me at the conference, and I was driving back from Melbourne to Sydney, and I hacked up a quick prototype in the car on the way home. There was no iptables rule generation or anything like that. The focus was really on the language. That was the thing that interested me at the time. Is it possible to actually have this level of expressiveness within a programming language when it comes to defining these firewall rules? And the question that I was really interested in asking is, what is the DSL actually going to look like? Is this actually possible? And then from that, what are the resulting data structures going to look like? Because that'll inform quite heavily the way that the tool is actually built behind the scenes when it comes to implementing like migrations and that sort of thing. So that's where Ript came from. It is just Ruby and iptables, in case you're wondering where the name comes from. So I built it in the 10-hour car trip on the way home. I answered the questions. To me, this was, the thought experiment was complete and didn't do anything more on it. So fast forward to 2010, I ended up actually being hired at Bulletproof. And within a couple of weeks of me being there, we had an outage, and I was sort of involved in the post-outage discussion. And I sort of raised some of these ideas that I had prototyped out a few years before. And I basically planted a seed within the infrastructure team about possibly better ways that we could manage these problems and improve the tooling. But at the time, we had bigger fish to fry. There were more important and pressing business problems that needed dealing with. So that was the end of that. Fast forward to March 2011, initial commit. Yay, actually working on this project. So it was a Thursday afternoon skunkworks project. We were sort of doing it off the books. So my manager didn't know about it, but that's cool. It ended up working out quite well for us in the future. So I was working with this other guy here who was in the support team. His name's Steve Fisher. He has a huge amount of organizational experience for how we want to do change management. And I sort of brought the iptables knowledge and testing experience to the table. So we did a bit more prototyping of the DSL, actually mapped out how we think that people would actually want to try and use it. Can you guys see that okay? Well, this is terrible. Is it possible to adjust the contrast on the... Hey, there we go. Is that a bit better?
It's too dark for the camera, I think. That's right? Nicht. And now the fog machine starts.
So then we tested the DSL. We were very focused on making sure that this tool was rigorous in the amount of testing that was around it, so that if we added new features that we didn't break stuff in other places. And we're using Cucumber to do that, to do outside-in testing. Hands up here who has heard of Cucumber or used it or... Okay, so a couple of people. Maybe if you've used Cucumber Nadios or something like that. So then we implemented this concept of migrations to allow the zero downtime changes that would compartmentalize those. And then we took it live a couple of months later, and now it's in use by some of our largest customers. So let's have a look a bit more closely into what Ript does. Let's have a look at the language. So at the very core, you have this concept called a petition. And a petition is a grouping of rules. So petitions are named, as you can see here. And within a petition, you have two types of things. You have labels and rules. So what are labels? Well, labels are basically a helper method for accessing information in a hash. It's just it's a way to look up data. So here we're saying that whenever I make reference to joeblogscode.com, this is the information, the metadata that's associated with it. You can actually pack extra random information in there if you want to do that as well. So yeah, with that, it's just a key, and then there's data that's associated with that. And the cool thing with labels and petitions is that anything that's actually defined within a petition is scoped to that petition. So it means that I can have two petitions here, one called Joe Blogs Co and another one called Foobar, both using exactly the same labels, but they're not going to conflict with one another. So it's all locally scoped, which is quite nice. Okay, so then we've got labels and now we've got rules. And rules is where we actually do stuff with these labels. So if we look at this here, we've added some rules, and we're saying here that that we've got a rule here for rewriting the public website, and we're saying that any traffic that comes into joeblogsco.com on port 80 is to be sent to app01 on port 80. And when Ript interprets all of this, it will expand those to actually be these real IP addresses up here. So this argument that we pass up here is actually purely a comment. It's not used anywhere else. We have some plans to maybe inject that into the rules themselves. So there's like a comment that you can have a look at. And it means that when you actually look at the raw iptables output, you can relate the rules that have been generated to the rules that are in here. But anyway, ignoring that. And then you have a bunch of arguments that you're passing here to this helper method. So yeah, we can add a bunch of these, and you've got rewrites and blocks and drops and that sort of thing. So the default policy within Ript is to actually just drop all the packets that you don't have an explicit rule for. So that has implications for rewrites. So this rewrite that we wrote here is great. It will do the rewriting of the traffic, but it actually needs an accept to be able to send that to even for the packet to even hit the correct part of the net filter stack in the first place. So what that would look like is you'd also have an accept here, and it's ignore that. That's actually meant to be an 80, and that would basically allow the access through in the first place, so that the packet could then be rewritten. But the nice thing about Ript is that it does all this stuff automatically for you. So that particular rule there is actually equal to this other rule. Ignore the 22, it should be an 80. So it's trying to do the smart thing for you. It has an idea about what you're actually trying to achieve, and it will go and do that for you. And again, this is part of dry, don't repeat yourself. On top of that, we can actually start cleaning up those rules a little bit more as well. So we have two rewrites here. Say we're rewriting joeblogsco.com to app01, and we're doing this for port 80 and for port 22. So we've got two different rewrite blocks that are doing essentially the same thing, but slightly different port numbers. You can actually just collapse those. So you have a single rule, and you can pass in as many different ports as you want in here. We can actually start, hello. Another device on this network is using your computer's IP address. Okay. So within this as well, we might have some sort of trusted SSH access. You know what? I'm just going to turn off the Wi-Fi, because it's going to keep doing this. Okay. So we're going to add a trusted office that we have in here. And again, this is for the trusted SSH access. So if we want to add that further restriction that you have on there, we just go from trusted office, and it refers back to this label up here, and it will generate that specific rule. Pretty handy. There are a bunch of shortcuts for doing things with ports. So as I said before, you have, say, ports 25 and 993. You can just pass them both in here to a single rewrite block. Then we can also do port ranges. So we can say port 6000 to port 8000 is going to be rewritten here. And this will do the smart thing actually behind the scenes. It'll actually convert it into the iptables command that just does a range. It knows that a Ruby range should equal an iptables range, so it creates that, rather than creating 2,000 individual rules. And then we have mappings as well. This can be pretty useful. So, if you're deploying some sort of Java application where you don't want it to bind to port 80, so on your firewall machine that's sitting in front of it, you say that okay, all traffic that comes into port 80 here should be sent to app01 on port 8080. Very simple. And we can actually combine all those together as well in a single example. The only caveat is that these mappings must be the last argument that's passed to that, and that's just a Ruby implementation detail. But just keep that in mind if you're using this. So then there's more expansive support for different types of protocols as well. So by default, the protocol that's actually in use is TCP, very simple. You can actually specify the numeric protocol number as well in here, but we sort of recommend that you use the string name. It'll handle the mapping for you automatically. There's a bunch of other types of rules that you can do as well in here. So we were just looking at rewrites, which is sort of the basic case that you're trying to do on these sort of firewalls. But you can add in specific drops. So you're saying here, this bad guy coming from this address, we need to drop it specifically. And we can also specify a range as well. Here we're specifying a /8, so we're blocking a large portion of China. And we're blocking here on UDP. So very common type of DDoS attack is a UDP attack. On top of that, there's extra little things, nice little things that Ript gives you out of the box. So you can pass log equals true, and it will actually generate all of the log rules that you would normally expect to be generated from this. Yeah, that's all you need to do. On top of that, you can actually specify log equals true up here on the petition, and it will cascade down to all the other rules that you define below it. And you can actually, you can do the inverse as well. So you can specify log equals true up here, and then specify false on the specific rule that you don't want logging for. So then there are shortcuts as well. So even more shortcuts. Shortcuts upon shortcuts. So if you want to do some sort of basic SNAP, you can actually just expand, or you can add an array here of all the different things that you want to do the SNAP for, and that will actually expand it into 3 different SNAP rules behind the scenes. So it's helpful when you're trying to not repeat yourself. You can also do other slightly crazy things, and I don't recommend doing this, but you can. So here we're basically creating a rule for every single combination of these 2 arrays. And you can, Ript will happily expand that for you, and that's cool. Okay, so that's a whirlwind tour of the DSL. Let's have a look at the rationale, though, behind why we're actually building this. So, as I was saying before, there was this existing tool to handle building the rules, but it did that in a pretty silly way, and there was a lot of downtime. And the core problem with that behind the scenes is actually the size of the changes that were being generated and needed to be applied. And really what this came down to was that there was a very poor separation of concern between different customers. So all customers were lumped into one big bucket. And if you needed to make a change for a single customer, it would have to affect every other customer. And this is just something that's baked into the design of the original tool. So how do we fix this? Well, rather than just looking at the technical challenges, we actually tried to take a step back and identify what the business really needed from firewall change management. And the core driver behind this is actually, it turned out to be increasing the frequency of changes. We have a set window in which we can make these firewall changes in every day. And the reason that we have this set window is because we expect that there will be downtime. So we want to be able to increase the frequency of that, but also limit the size of those changes so that hopefully when we're making these changes, they're going to have less effect on both that customer, but across the whole infrastructure and all of our customers on it. And what we're trying to do actually is just reducing and removing as much friction as possible from this change management process. Doing things early and often, hopefully we'll end up catching problems sooner. And what we're trying to really do here is improve the quality of the whole change management process, which means that we can increase the confidence when we're actually making these changes. And this is really important for the people that are at the coalface that are making these changes, these engineers that are tasked with making these changes. They don't want to have to use a tool where they're afraid that it's going to blow up every second day on them. We want them to be confident when they're making these changes. And you'll notice that all these principles are actually just principles behind continuous delivery. Who here has heard of continuous delivery? Hands up. Okay, a couple of people. Well, I'll explain really quickly what it is. So firstly, you should go and have a read of this book by Jess Humble and Dave Farley. It's a really simple and easy read. But the core idea behind continuous delivery is this. So you have these different phases when it comes to delivering software or changes, whatever that might be. So plan, coding, building, testing, blah, 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 all the way up to operating up here. So there are some other terms that sort of fit under the continuous delivery umbrella. So the first one here is just agile development, whatever that actually means. And that basically, the idea is that agile will take you from the planning to the handoff of the build and testing phase. Then you have continuous integration, which will take you one step further. It'll take you to the testing and the releasing phase. And then you have continuous delivery here, which takes you up to the releasing and deploying stage. So then on top of that, maybe you've heard of this DevOps thing, and the idea is that maybe DevOps sort of encompasses all of this, and then it sort of provides a nice feedback loop all the way back to the beginning. And this is really important in the world in the industry that we're working in today, which is, if you look back at how ISPs and telecoms have traditionally dealt with making changes like this, they have very specific change windows, right? So there's a period of time every day or every week or every month of which you can make changes, and you can't make changes outside of that. And the idea is that you contain the failure to that, and then hopefully, the failure won't be so bad. But in the modern world that we're sort of living in now, the industry as it's evolving, the change windows that we have are actually 24/7. Businesses don't particularly like the idea of having to wait a long period of time between them submitting and asking for a change and it actually being implemented. Like a really great example from our perspective is so our change windows run from 4 p.m. in the afternoon to 6 p.m. in the afternoon. So if a customer submits a request for a change at 3:45 in the afternoon, so 3:45, there's not going to be an engineer to deal with that change. So that means that although there is a change window coming up, that change probably won't actually be implemented for up to 24 hours after that. And that has all sorts of interesting implications because maybe by the time the change has been implemented, the customer requirements have actually changed, but they haven't communicated that. Just from a service provider perspective, you have that delay in there. You want to be able to deliver the service to the customers as quickly as possible. And this really comes down to reducing risk, and not so much technical risk, but maybe business risk. It's risky to be slow when you have competitors that are faster than you. So we want to be fast, like our competitors. And then you have this open source idea of releasing early, releasing often, and then failing fast and recovering quickly from if we make changes and they fail. So, how do other people solve this problem within the IT sphere? So what we're trying to implement here is some form of incrementalism, so making small changes very, very quickly, and we want to make them nice and small. And what we're trying to do in the iptables world is actually taking a current unknown state, potentially unknown state, and migrating to a desired state, sort of like what Puppet is doing when you do a Puppet run on a machine, and it will analyze everything that you've told it to do, and it will try and work out, okay, these are the things that actually need to change. So yeah, migrating from this current state to this desired state. So has anybody here used Active Record at all? Hands up if you use Active Record. Okay, one person, that's good. So Active Record is an object relational mapper in Ruby. It's actually it's basically the database access mechanism in Ruby on Rails, or one of them at least. So Active Record has this other thing called migrations, and migrations are this, but we can just summarize it. So we want to be able to describe some sort of transformation to data or to state. And we want to be able to execute that change against, in this particular case, a database, but maybe it's some sort of system that we're maintaining. And we don't necessarily know what state that system is currently up to. So we want to be able to have a tool that is able to make these sort of changes incrementally to something that we don't know about. So in Active Record, the migration looks like this. So you have an up and a down, so going forward and going back. So in this particular example, we are adding a column. to the accounts table called SSL enabled, and it's a Boolean. And then for rolling back that change, we're just simply removing that column. So there's another database migration tool in Ruby called SQL, which sort of does something fairly similar to Active Record. And it has exactly the same concept with an up and a down. Maybe it's a bit more Ruby-like in the DSL. You notice that it's sort of similar to Ript, right, in the way that it's working. But SQL has this interesting feature where you can actually just do change. So you're defining what you want the state to be at this particular point in time. And SQL is smart enough to work out how to actually go back in the other direction. And again, this is sort of looking fairly similar to Ript, right? So migrations within a Rails project, you have like a database migrations directory, and then you have a bunch of files within those. And then when you run the database migrations, like this, against a particular database, say a database that's sitting on your localhost, it will run through all of these sequentially. Well, actually what it first does is it works out where the database is currently up to. And let's say it's at 009. It will then run through all the migrations beyond that. So there's a pattern. There is an established pattern for solving this problem. So we want to try and use the same sort of ideas. Okay, enough talking. Let's actually have a look at the tool. Okay. Right, so I'm in this example rules directory here. So if I go sudo ript rules generate, ooh, that's nice. Here we go. Make that full screen as well. Rules generate. Okay, so what that's done in my local directory here is I have these two files. I've got this bootstrap.rb, and we're using this special raw rule, which I might talk about later. So here we're setting the default policy. We're using some magic to actually to scrub a bunch of traffic and create these low-level rules that Ript then depends on, which I'll talk about in a moment. So we can pretty much just ignore everything that's in this bootstrap file. But let's have a look at OSDC. So within this OSDC petition, we have firewall 01, app 01, and app 02. There are a bunch of addresses that are associated with that. We've got a rewrite rule, so we're saying for this public website, when traffic comes in on firewall 01, DNAT it to app 01. And the same thing for doing an SNAT for the outbound as well. So if we go and have a look at those rules themselves, if we do a generate here, it will parse everything that's in that directory, and it will create a bunch of iptables rules, as you can see here. So it's translating that Ruby DSL to these iptables rules. So from here, I can then do a diff. So I'm going to do a diff here, and it's saying that there are no changes because I've actually loaded these up previously. So if I do an iptables minus ln, you can see here that all this stuff has actually been loaded into the kernel. So what diff is actually doing is pretty cool. It's actually running the generate command and then looking at the live state that's loaded into netfilter in the kernel, and it's generating a diff between the two. So when it actually comes to applying, making some sort of change, let's say we want to add that one there. So I'm going to do a diff, and it's gone, oh look, we have some new rules that we need to insert here. So, do an apply, let's run that, and I will do the diff again. That's it. That's how simple it is. Okay, so, it looks so magical. How is it actually doing this? And it's true, it is a little bit of magic behind the scenes. So obviously it is using iptables. And just to do a really brief primer of iptables, it's slightly simplified. On the filter table, you have an input, forward, and output chain, and you can see what these are for. So for delivering packets locally, for packets that are being forwarded someplace, or packets that originate locally and being sent someplace else. Then we have a NAT table, and to incredibly simplify what pre-routing and post-routing do, they are packets for DNAT or packets for SNAT. So, within Ript, we have a bunch of Ript-specific chains that allow us to perform this magic. So there's this first chain called before A, and before A, you're doing traffic scrubbing. So things like ICMP, stateful packet inspection, keep alive, conmark, that sort of thing. This is a boilerplate chain. You will almost never, ever have to touch it unless you have some very specific requirement, but it's very easy to do. It's very easy to just open up and add some extra rules in there if you want. So then we have another chain called partition A. And these are pointers to the specific partition chains that we were defining just before. So all three of the input, output, and forward chains will actually jump into this partition A chain. So if we have this particular customer-specific chain here, all of those customer-specific rules will live in a nice compartmentalized chain that is separate from everything else. And the rules will actually point into that chain there. And there's actually information metadata that's encoded into these chain names. So the first part is the partition name, obviously. Then we have the rule set type, so access, DNAT, or SNAT being A, D, or S. And then we have a hash, and that hash is calculated by interpreting the DSL, generating all the rules, and taking an MD5 checksum of that, and then we shove that into the partition name here. So we have these fundamentals. How do packets actually go from being generated someplace on the internet to being sent to a target machine? So we have the standard input, forward, and output chains that I was talking about before. They all jump into this before A chain, which is doing the traffic scrubbing. Then they jump out of the before chain, back into the input, forward, and output chains, and then into this partition A chain. Then within the partition A chain, you have all of these pointer rules. So these are for different customers with different partitions. And what will happen then is the packet will then try and match on these pointer rules. So it'll go all the way through here. And then if it doesn't match on anything, it will then jump back out into the input, forward, or output chains, where the default policy is to drop the packet. So these pointers, as I was saying before, jump to these partition chains. And these pointers are actually for each source and they match on these source and destination. We don't match on protocol, port, connection state, or anything like that. And the idea is that we want to make the traversal of partition A as quick and simple as possible so that the kernel doesn't have to do all that much work. So if we have this partition A chain with a bunch of these rules here, it's going to try and match on this pointer rule. It doesn't. Goes through, doesn't match on any of these. Oh look, it matches on this one down here, ABC radio. So from here, it will then jump into the ABC radio chain. So then there is a verdict rule. So this is where all the low-level specifics that we were defining in those partitions come in. So we do things like logging, accepting, rejecting. So the packet will then try and match these verdict rules that are within this chain. So it's not going to match on this one, not going to match on this one. Oh, look, it matches, so we're just going to reject it. Then you have logging, which is actually a bit of a special case in that if you have a particular packet that's coming through that's destined for, say, 117 ending in 72, it'll actually match on this, but then it's not a true verdict rule in the iptables world. It's a little bit of a lie. It'll actually match on this, log something, but then return, and then it'll do the accept. And this is how we do zero downtime migrations, having all this compartmentalization. So let's chain all of this stuff together and look at how it actually works in the real world. So when I run a Ript rules apply, what it will do is it will just take the new partition name and the pointer rules and insert them at the top of this partition chain. That's it. We'll just keep inserting those pointer rules. So they will always be inserted at the top of the partition A chain. They will never be inserted at the bottom. And the ordering is actually really important. It's an implementation detail that you probably don't need to care about, but it's good to understand it. So the problem that we have here, though, right now is we've inserted these new pointer rules, right? And you notice that there are actually overlapping pointer names. You have two customers with the same partition name, and there are two different partitions that they point to. So that could be bad. And why could that be bad? Well, let's look at here. We've got this new rule that we've added. This new rule set that we've added in this updated partition for the same customer name. And we've got this accept rule here, and maybe a bunch of other rules. So the packet has jumped into this, and it hasn't matched on any of these rules. So what's actually going to happen is it's going to jump back into this partition A chain. But then it's actually going to jump right back into this old partition chain, which is bad, because you have this lingering state right there. And you might actually have an accept on that. So this is bad. You've got two sets of rules that are inserted at the same time with different behaviors and an older behavior that you might not actually want anymore. So it hits the old rule. That's bad. We don't want that. So you need to clean the rules. And this sounds, onerous and difficult, but Ript makes this really simple. You just run that command and that's it. So it's the only downside of the of this architecture, but there's a nice simple helper to help you do this. So when you do a ript clean apply, it will identify the identical partition names, and then it just blows it away. Look, another one, gone. So hence the ordering of these pointer rules is really, really important. Okay, so this is like the lower level workings of the tool. How do you actually go about using it within your business and your day-to-day? So this is actually really simple, as you may have sort of deduced already. There are only three core things that are happening when you're actually wanting to make these rule changes. You're doing a git pull or a bzr pull or whatever the revision control system is that you're using. You're sucking the latest rules down into a particular directory. You're doing a diff to work out what are the things that are going to change, sort of like the no-op mode in Puppet, and then you do an apply. That's it. And let's just ignore the clean and the...
When do you do apply without clean?
What was that, sorry?
When will you, under which conditions will you want to do an apply without a clean apply? So why isn't it always a clean apply?
Okay, that's a very good question. So the question was, why is the clean apply not the default behavior when you just do a ript rules apply? Is that right? Yeah. Okay, great. So you can think of ript as being a little bit Git-like in that it will break all the different functionality up into separate commands, and it's up to the operator to work out how they want to chain those commands together. So you're absolutely right. In the way that you would be using it, you would always be doing the rules apply and then the clean apply, but we keep them conceptually separate just for ease of maintainability. But that's really important actually when it comes to this real-world example. So what's the workflow that we use for this? We've been using this for over a year now. So we use Puppet to install Ript on the target firewall machines in our firewall platform. And then we have a separate repository, and it's called ript.rules, and it's just a standard Git repository, and we basically have a subdirectory in that for every separate firewall pair within our infrastructure. So why do we keep all of our eggs in one basket? Well, the main advantage for us is that it becomes very easy to migrate customers between different firewall pairs. All you have to do is a copy of the file or git move, and then you retain all of the version history for all the changes that have ever been made to that particular customer's rules. And then we use Capistrano. Who here has used, has even heard of Capistrano at all? Hands up. Okay, cool, a couple of people. So Capistrano is basically SSH in a for loop. It's very, very popular in the Ruby community and web development community for deploying web applications. We happen to use Capistrano all over the place for lots of system-specific tasks. If you're at Puppet Camp tomorrow, I'm talking about that a little bit more as well. So we use Capistrano to deploy those firewall rules, that git checkout, into this directory over here, etc firewall current. And we just do that with the cap deploy. So when you do a cap deploy of the new rules, it's actually running a ript rules diff, and it will not actually apply anything. Then if I run a cap deploy with apply equals true, it will do ript rules apply, and it does a ript clean apply as well, and they're nice and separate. So that's how you chain all those different commands together in a workflow. Okay, other workflows for people who are not crazy like us and using Capistrano. So mcollective is another approach here that we've been investigating a little bit. So you replicate exactly the same format where you're just doing a git pull ript rules diff, and Ript rules apply. And then you would just write an agent that would do all of this and handle the coordination across all the different machines in your LVS and firewall platform. And then you have the other option, which is Puppet as well. And the only reasonable way to do this at the moment, and perhaps it's a little unreasonable, is that you have lots of templates that are generating Ript's Ruby DSL. And that's pretty dirty. You don't really want to do that. Maybe you're writing like a custom Puppet type to handle the generation of those rules. That's a bit nasty. We can talk about that a little bit later if I've got enough time though. Okay, so this isn't all rainbows and unicorns. There are significant challenges in writing a bit of system software like this, which might be interesting if you are writing low-level system software like this. The first major problem that we've come across when writing this is how do we test? So we're using Cucumber, which is like a natural language testing tool that allows you to write at a very high level what you expect to be able to do with the tool. And then it takes an outside-in approach where you're not like testing the lower level units of the actual program, you're actually running the program on a live system and seeing how it behaves, capturing the output. And we rely on this incredibly heavily. In fact, we practice test-driven development whenever we are adding new features or even fixing bugs. So there are huge amounts of examples that are all used within the tests within Ript itself. So in fact, within Ript, if you do an ls on examples, we have 41 different tests that are shipped with it that test all the different behavior that you could expect out of Ript. Within those, there's probably close to 100 individual tests. So we care very, very deeply about testing when writing this because we want to make sure that it's correct, especially when you're managing things like firewalls that have large, expensive customers hanging off them. And this introduces some interesting problems that people who write systems code deal with. And it's a bit of a tricky problem that maybe you don't have if you're dealing with like higher level programming, like building applications or web apps or that sort of thing. And the problem that we were frequently coming across is lingering state. So what I mean by that is you would go and write a test to verify a new behavior that you are trying to implement within Ript. There would be some sort of bug in Ript that the tests would execute, and then you lock yourself out of the test machine because you've suddenly blocked all traffic. That's happened a whole bunch of times. So we ship this rake task called clean slate, and we have a trigger in the test that says after you run these tests, it's even before that. So we say that if the tests are being run, then in 60 seconds, run this rake clean slate command, which will undo whatever damage you've managed to do to the local machine. And it means that, like, worst case, you will be thrown out of the machine for 60 seconds, but that's okay. So open sourcing. This is an interesting challenge because we always intended to release Ript as open source from the outset. So we love open source. We're using it absolutely everywhere. But there was a business-specific requirement, which is that we wanted to build a minimum viable product. We needed to get something out and delivered so that we could stop experiencing the pain of the older tool. So this meant for us that we started very, very concretely. So we looked at the specific business cases and the problems that we were dealing with, and that sort of meant that we put these hard-coded references to different things within our infrastructure, within the Git repository, and that was okay because the idea was that when we came around to open sourcing it, we would want to scrub these internal references from within the tool, and we would do that by looking at the Git history and trying to rewrite it. So it all sounds pretty reasonable. It turns out that this was not a good idea at all, because the problem is that you need to try and keep track of state within every single rewrite to make sure that it's all internally consistent. It's basically referential integrity. That's what you're trying to ensure when you're rewriting this history. So our only real recourse for this was to actually just nuke the Git repo and create a new one and then just do a blind import without any revision history. So we actually maintain another repository called ript.history. And you can see here that it has 234 commits in it. Then we have the ript.public, which is what's published on our GitHub account, and it currently has 12 commits in it. So that sucks. Obviously, it's not nice to just drop a bunch of code out into the wild and expect people to just not have any history or know anything about where it came from. What we tried to do, though, is we retained a change log. So every time we make a change, we have a strict validation process when we want to push out a new release, and it will verify that the commits that have been made, there is a change log reference for it. So we've had that for quite a while within the project. So we try and make the changelog messages as descriptive as possible, so that if you're having a weird bug and you think maybe it's a regression, you're able to at least go through the changelog here. So one of the other challenges is the interface, and this comes back to building this minimum viable product, trying to start very, very concrete. So that interface is this bin file called Ript, and it's a little manky, a little janky. Let me actually show you what I mean by that. Okay, so I'm running this sudo ript rules diff, okay? And before I had the dot here, so it's saying operate on my current directory, and I'm going to delete that. This is not a user-friendly error message at all. So we've sort of got around it by making sure that we have a process that's built around this that we use, and it'll always pass the correct inputs to it. But this is not nice from a new user perspective. If you run that, you would expect to see some sort of help prompt. So we're actively trying to work on that and make that better. And it's on the roadmap. We basically want to gut the internals of the current interface and make it nice and easy for people to use. That presents some interesting challenges, though, in that we don't use one of the cool things about Ript actually is we don't use any external libraries at all. We just use the Ruby standard library. So it means that it has a very, very small footprint when it comes to deploying it on your servers. It means the side effect of that, though, is that we can't use any of the nice libraries for building nice command lines under Ruby. So, obviously, IPv6 is a wanted feature. There is no current support, but we consider this to be really important. We're actually moving to IPv6, providing IPv6 hosting for all customers from about the middle of the year onwards. So right now, internally within Ruby, within Ript's Ruby DSL, we have this toIptables method, and it will take a rule definition that is generated from the DSL and turn it into an iptables rule. So to add IP6 tables support, we just add a toIpsixtables method, and we'll generate the correct method. Oh, sorry, it'll generate the correct command, and it should be fairly simple to implement. It also means as well, if you're managing, say, BSD firewalls with PF and that sort of thing, you could, in theory, implement a toPF method, or like weird Cisco firewalls, you could do toCisco. But this talk is really about writing our own history. We found that it's vastly too easy to complain about the tools that you have been handed by your distribution. And we really wanted to question our circumstances of why we were feeling the pain of the tools that we were dealing with. So if we're working with crappy tools, then why are we working with these crappy tools? What led us to this point where we have all of this pain? Obviously, when we selected the tools in the first place, they made a lot of sense. We wouldn't intentionally choose tools that would cause us pain. So what has changed between selecting those tools and what we're doing now? What is the problem that you're trying to solve? How has that problem evolved? And for us, the tools are really a means to an end. They can be rebuilt, replaced, rewritten. And for us, it was very much about finding what our concrete principles were. And that was increasing the frequency of changes, reducing the size, and reducing the friction. So, thank you very much. All right, any questions? Yes? Just 1 second.
Can Ript coexist with other iptables too?
Okay, yeah, so the question was, can Ript coexist with other iptables management tools? The short answer is no. So we assume that it is the only thing that is managing rules on your system. Any other questions? If there aren't any other questions, I have some more interesting slides, a bit of navel gazing as well. All right, I'll go down that path, given that nobody's putting their hands up. Okay, so let's have a little bit of a sneak peek at some other things that we've been playing with. So these are pretty important questions. You know, what about self-service firewalls where we want the users to be able to make their changes? You know, wouldn't it be great if we could remove having an engineer having to write code for some user request? How does this work with configuration management? I was sort of alluding to that before with Puppet writing out a bunch of ERB templates. So you use Puppet to write code which gets translated in Ript, which turns it into iptables commands. That seems pretty insane, right? And the question we're really asking here is how do we have some sort of auto generation or smart generation of these rules? So there are simple ways you can actually do this right now. Ript is just Ruby. The DSL, in fact, is actually just Ruby. So you can do. Can we dim the lights again so people can see the slides? Thanks. Right, so we just have an array here, Ruby array, and we're iterating through these, so we can actually dynamically create these partitions with, in this particular case, the same information. And that's maybe a little crazy. And it's a little bit contrived as well in this example. You will probably have some sort of hash that you're iterating through that has the definitions of these labels and these rewrite rules and that sort of thing. But you can do this with Ript. It's fundamental. In theory, it is possible, except that we explicitly disallowed this because we consider this to be an anti-pattern, and it's difficult to maintain and understand. You know, if you have some sort of system here that is, say, you have a call using libcurl or nethttp in Ruby that's fetching the definitions for some sort of configuration management database, and then it is iterating through those to actually generate these rules. It sort of obfuscates what the intention is. So we want to disallow that. However, you can actually pass an I am a Ruby dev equals true to it, and it would allow you to do this insane thing. But this is an interesting idea. Like this, while this is a hack to get around the limitations, there's actually a lot of good substance to it. So let's go deeper. Here is vaporware. Nothing is written, but there's all the discussion for this is happening out in public. So if you look at the GitHub issue, number 5, it's called Read Ript Rules from JSON. So if you look at these petitions here, using the Ript DSL, it looks fairly data heavy, right? You know, they just look like a simple DSL around manipulating different types of data. So can we map that data into real data, like JSON? It turns out that we can. The DSL maps very, very nicely to just normal hashes, strings, integers, and arrays in JSON. So that presents an interesting question. Firstly, we have a couple of interesting questions. Firstly, we want to be able to take existing petitions that are written in Ript and call, to JSON on that, so people can migrate away from using the pure Ruby DSL, having other systems that are actually generating JSON and know how to do that. And we can do other interesting things like including some JSON in here. So you might have some core definitions that you don't ever want to change, but for this bar petition here, you want to read in some external JSON that's dynamically generated out of your configuration management database like PuppetDB or Chef's databags and that sort of thing. So then, can we take that even further? Can we decouple the DSL entirely from Ript? So Ript then becomes two almost separate projects that are sort of related, where you have a tool for defining what you think the rules should be, and another tool for taking that definition and actually applying the state changes, the state transitions. So then the DSL would just be generating JSON, and Ript would be then consuming that JSON. So then you can think about the DSL being very useful for the simple cases where, in fact, most users who are just using the DSL would be completely unaware that the JSON is being used behind the scenes, but that's what Ript is doing. And then if you want to inject your own JSON into Ript, Then you could write some other tool that would generate those rules and then pop them in place. And then Ript would consume those and apply those. That's sort of interesting from a dynamic infrastructure perspective. And it's even more interesting when you take orchestration into account. So, possibly the elephant in the room, with all these changes that we're making, we're taking all of these interesting ideas and concepts from software development and we're applying them to writing systems tools. How do we handle testing changes? Because we seem to be doing a pretty good job of using those tools, except we're missing a fairly core thing from a core ideal from software development, which is actually testing the stuff that you're writing. So if we're testing Ript, then why aren't we testing the rules that Ript is generating in production? So mcollective could actually be a really good fit here, where you're writing an agent that is doing these three things. So let's look at a mock scenario. You have three firewalls in a firewall platform, and Ript is running on these three firewalls here. Then you have a border router that's sitting in front of those, and that's connected to the rest of the internet. And then you have a bunch of IPs that are assigned to each of these firewalls here. And then you're using something like OSPF or ISIS to advertise that these machines have these IPs. And the border router is doing intelligent routing. And there's priority that's attached to each of these announcements as well. And then you have traffic that's coming through, and maybe you have an active-active setup where you've got all the traffic going through firewall 01 and firewall 02, and then you have firewall 03 as a hot spare, I suppose. So if we're using mcollective here, what about applying the rules to firewall 03, sending these rules out to some sort of external agent that exists outside of your network, which is then hitting border 01. Border 01 knows to send traffic from that agent through to firewall 03. And then you're testing that traffic there. You're validating whether the rules that you've written actually work externally. That's a pretty powerful and interesting idea. Let's say they fail. So what happens then? How do you recover from the situation? Well, it's actually fairly simple. You just say, go back to this previous revision and go and apply these rules here. So that's simple, easy. What about in the case where, so you've made these changes and you've worked out that they don't quite work the way that you expect, and you've gone and refactored the rules, or maybe you fixed your tests and then you've deployed these rules and it turns out that everything works okay. So then you just use mcollective to roll those same rules out to all the other machines in the firewall cluster, and then that's it. Fairly simple. And from a user's perspective, there are two ways to look at this. From a user's perspective, you would run a single command after checking in, or in fact, maybe not even that. Maybe all you would do is you would check in your firewall changes, you would git push them, which would then make a call out to an mcollective client that would then trigger off this entire deploy process. Or maybe you have some sort of external system that is feeding the data into mcollective here to roll out these changes across your firewall cluster. So it becomes very hands-off. You don't have to actually maintain anything here. I sort of find this to be a pretty interesting idea. So we can take that even one step further, where we're reading the Ript rules from the JSON. What happens if we actually generate that JSON and then push it to those target firewall machines with mcollective? And it means that we have no checkout of the rules on firewalls, which is an interesting security consideration right there. And we compile the rules within an mcollective client and then push them out to the set of firewalls. It's nicely segregated and secure and relatively dynamic. So, thoughts if anyone is interested in talking about that? Nope. Okay. Any more questions or comments or anything like that? Okay. Well, if you're shy, come up and talk to me after this. Thank you very much.
Okay.